Great. So welcome to another session from the Portland Python Pirates. My name is Chris Thompson. I'll be leading this particular session. And actually, this is a series that we're running, or that I'm running right now, where we go take you from introduction to containers, and specifically we'll be using Docker, all the way up through Kubernetes. And this is meant to be introductory. We are going to get technical, but I don't want that to turn you off. So hopefully we reach as wide an audience as possible, those with a deep technical background and those who are like, I don't even know what a server is, right? Like, hopefully we can reach everybody through this. I've done similar tutorials before, but I don't think I've done a specific like Docker to Kubernetes tutorial. I think we've done like cloud deployments and things like that. And you can find those videos on our YouTube channel. There's not many because I didn't realize that I should have a YouTube channel until like like last year or something. So there's like, dozens of videos that we don't have on there, but there is some good content on there, and we're posting all new material on there. So this will be recorded and posted on our YouTube channel as well. And we also have a website, pythonpirates.org. You can sign up to give a talk. There's also a pretty robust list of Python resources there, and we'll be adding some container resources as well. And I'll be mentioning some during this talk. The organizers of this meetup are myself and Brian Holman. I don't see him jump in, but I was bulk adding people, so he might be here. But you can reach out to either of us on LinkedIn. We're happy to connect with people. If you also need technical assistance or anything like that, we are in the Slack channel, and there's a link to sign up for our Slack channel on the website. So pythonpirates.org, go there. There should be a link pretty obvious to join the Slack channel. It comes and goes how much conversation is in there, but we're always available and always happy to help. So our guiding principles, we're inclusive, we're Python focused. We do try to do progressive learning. So this is kind of a microcosm of that, where we start really basic with containers. What's a container? How do we use them? All the way up to orchestrating containers, right? Kubernetes. So we try to do this kind of progressive idea, take people from point A to point B, and we're collaborative, right? So if someone has something interesting to add, if you have any questions, comments, if you want, you can drop them in the chat or do a hand raise, and I think should show up on my screen. I'm monitoring that right now, so feel free to jump in at any time. Okay, so the agenda, we're going to talk about the history of containers, virtualization and containers. We'll talk about why you should use containers, right? And they're not necessarily right. Like, I'm not going to say that you should always use containers, but I will tell you why you should use containers, when you should use containers. What Docker is, right? We've all heard of Docker. Maybe some of you have used Docker, but we'll talk about what Docker is. And then we'll actually do a demo, and I will drop the link for the repo. In fact, I should probably do that. Give me 1 second here. I should have that up. I'm gonna jump out of my slide deck for a second. I will drop those links in here.
Are you going to include the slide deck in your along with the video?
Yes. I will share that.
Thanks.
I'll probably share it, if it's okay, in the comments of the YouTube video. I guess I could drop it here too. I could just share it real quick. That's not a problem. I'll do it right now while we're thinking about it. I'll do both. Anyone with the link can view, copy link. Okay. Let me drop that in the chat right now. Okay, so there's that. That's the slide deck.
Thanks.
Yeah, no problem. And go back to the slideshow. Okay, we're back. All right, so some resources that I really like, and now that you have the link, I won't bring them up, right? Click on these, but these are hyperlinks to the actual resources. So there's a bunch of tutorials on real Python pertaining to Python and Docker or containers in general. So definitely check that out. Tons of stuff there. Docker Up and Running 3rd edition is actually out this month. This was the original book that I read to learn Docker in the first place, like years and years ago. And it's super, super useful. I haven't read the new one, but I assume it's very useful, right? And Docker has changed quite a bit. Okay, so it's definitely worth checking out all the new stuff that's in it. So being that this is out this month, it might be worth picking up. I'm always an advocate. I think O'Reilly is one of the best subscription services to have. You get access to all O'Reilly books, Manning, like all the big publishers. And so you would have access to this book as well as soon as it comes out. You also get early access to books. So as books are being written, you can check stuff out too. So definitely check out O'Reilly, but specifically Docker Up and Running 3rd edition. And then Python Speed is a website that I've used in the past. I really like it. I forget the guy's name. Forgive me, guy who wrote the awesome website. But they do. It's exactly what it sounds like. It's a website talking about how to speed up your Python code, right? And he does a lot of stuff on Docker too, containerization but optimization of your Python running inside containers, which is super, super useful, right? As we're moving containers into production, which we'll go over in all 3 of these tutorials. Great, yeah. And I should mention too, Docker's documentation is phenomenal. Like it is really, really good. It's very informative. So don't hesitate to also just jump into the Docker documentation as well. Okay, so talking about the history of containers. When we first started, right, long time ago, it seems like now, it's only like 30 years ago, but long time ago, maybe longer than 30 years, 40, 50, I don't know. Anyway, pick your timeline, but long ago, we started with hardware, right? We had servers, we had rack of servers. Now we still have those, don't get me wrong, but this was the go-to, right? So racks and racks of servers. Some of you may remember these days. The pros with this, right, where you get a server, you rack it, you launch your application on it, and that application is isolated de facto, right? And you then network it with other things that it needs to talk to, and that's great, right? And because it's a single server with a single OS and an application running on it, right, it's easy to manage, right? Like it's, you have one thing to worry about. Now, of course, when you're scaling your application, you may get multiple servers running multiple versions of the application. And then, obviously there's complexity that comes along with it, but lower complexity, right? Like it's all hardware. It's all like, oh, we need a new app, or we need a new version of the app, or whatever. Oh, we get a new server, we rack it. There it is, right? Everything was kind of analog, we'll say, right? Quote unquote. Now, what ends up happening, right? Like there were some cons to that. One of the cons is low resource utilization. So with a server, right, there's a lot of space on there that if you're running, say, a Java application or say, a proxy, right, or something, there's a lot of, resources on that server that are underutilized, right? And that's a problem. So you might be using 20% of the server, right? But that other 80% just kind of goes unused, and that's not great. Slow to scale. So if we want to scale our application, we got to rack another server, right? And that takes a long time. You got to ship the server, you got to buy the server, you got to ship the server, you got to rack the server, right? So you can't react to demand for your application as very fast or very quickly. It's expensive. Servers are not cheap, right? And maintaining those servers is not cheap, especially as it grows larger and larger and larger, right? You get more and more servers. It becomes very expensive to maintain, and your capex goes up. You have a lot of under utilization. It's it can be very expensive. And another thing is, it only allows single version dependencies. And what I mean by that is, like, so say I want to run, say we have Python 3.10 and Python 3.11, right? Well, we have like things like virtual environments and that kind of thing, and that's cool. But kind of running that on a server, right? It's difficult to have multiple dependencies, right? Python kind of solves that, but like having multiple dependencies on a server can be a headache. And so, if you want to run different versions of the same package, that can start to become cumbersome for your IT department. So along comes virtualization, right? And this was this blew everybody's minds. It's like, well, now what we can have multiple virtual machines running on a single. So you have your. Let's back up. We have the hardware layer, right? So think of this as your server. You have the host OS, so it's still the same. But then we have this hypervisor. So what this hypervisor's job is like, so you think like VirtualBox, VMware, all of those. Their job is to virtualize computers on top of the host operating system and the hardware, and allocate resources for each of these virtual machines, right? And what that allows us to do is increase that utilization, because now we have isolation, right? You can have these VMs talking to each other, and that's not to say you can't, but now you can have multiple versions of an application, right, running on a single server, and that's really great. Right? Because now we can have like our job, one single version of our Java application, like 3 different instances of it running on the same hardware, or, right, we can have different versions running on the same hardware, right? Which solves kind of that dependency problem. Again, back to that utilization problem, it makes that easier. And now each of these virtual machines is essentially a computer, right? It has its own OS, its own operating system, own directory tree, on processes, so on and so forth, right? These are each individual servers themselves. And so the pros, right? Running multiple operating systems on a single host. So this might be Linux, but we can run a Windows computer on top of a Linux system, right? So we can, and vice versa, right? And then we can, replicate that across, right? Whatever we're using, like CentOS or, RIP, but CentOS or Ubuntu, let's say Ubuntu, that's probably a better one at this point, so on and so forth. Multiple apps or multiple versions of apps on multiple hosts, right? Which we just talked about, and the better resource utilization, which we also talked about. Now, the cons are you have multiple OSs, which is resource intensive. So because we have to run these OSs, right, a full operating system, that can get expensive in terms of utilization. So even though we're able to better partition our resources across these virtual machines, they're still being, those resources are actually being sucked up by a lot of our guest OS, right? This operating system, whatever it may be. And so we're still not maximizing our utilization. We're doing better, but it's not as good as it could be. We get redundant or unnecessary libraries and dependencies. So because we're running this full guest OS, and there are, smaller versions of these OSs, but in general, right, because we're running these guest OSs, these are full versions of a OS, right? And because of that, we get all the libraries that come along with that. Now, if we're running just a Python application, we may not need all of those libraries that are there. And there's 2 things that happen there. And one is, again, resource utilization, like unnecessary packages equal too much resource utilization, right? Going wasted, right? Wasted resources. And then the other thing is our attack surface. So security-wise, right, all of a sudden we have a much wider attack surface that makes our apps more vulnerable to attacks. Now, of course, everybody's like, well, you have to bust through here and kind of go, then you have to get into the virtual machines and blah, blah, blah. But nevertheless, right, you want to minimize that attack surface as much as possible in all areas of wherever your application is running. And because you have all these packages and libraries that need to be installed, right, to run the OS in the first place, it kind of widens your attack surface, and that's not great. And then slow boot time. So even though we can spin up these virtual machines, it's still slow to spin up these virtual machines. Like you have to do you have to wait quite a bit. If you've ever used virtual machines, it can be anywhere. It's in the range of minutes, right? Hopefully not tens of minutes, but it can be, right? And so reacting to demand, you're still slow to react, faster than you would if you needed to wait a couple weeks for a server to arrive or whatever. But nevertheless, still slow to react because of these slow boot times. Nice. Finally, right, moving beyond that, we have containers. And containers kind of address all of the problems that we've talked about, both with bare metal and virtual machines. Okay, so I put these side by side, and I may have grabbed this image, I don't remember. But anyway, they're side by side, and we can see we still, we have the hypervisor like we just talked about, the binaries and libraries and so on and so forth. But here, right, what we're able to do with containers is we skip out on this hypervisor and we replace with a container engine, a runtime such as Docker. There's also others such as Podman and like Rocket something, but the most popular is Docker. And what Docker will do is, instead of installing an OS like you would on a virtual machine, you actually are cordoning off resources from the host OS, right? And just allowing, by utilizing user spaces, or we'll go a little farther than that and just say namespaces, right? And C groups. So namespaces allow us to run processes isolated from the host OS, okay? And C groups allow us to control resources, so that there's not, you're not starving out other processes. So in essence, what a container is just an isolated process that's running, and it utilizes, the container engine allows it to utilize the host operating system, the resources from that. But they are also isolated, right? So unless you define, hey, this container can talk to this container, or this container can talk to the host in a privileged way, it doesn't know that it's a container. So you actually have a lot of similarities with an operating system. Like if you go inside of a container and you start poking around, it feels and looks like you're in a full operating system, but in fact, it's just the binaries and libraries, right, that are then using the host OS libraries. And what that allows us to do is slim down these containers, because we don't need all of those libraries and binaries to run a full OS. We can cut them down to almost exactly what we need for our application, which solves that thing we were talking about before with the attack surface, first of all, right? And that's not to say that containers don't have their security vulnerabilities, but that being said, you can slim these down to where the attack surface is much, much smaller, right? And then, the other thing is resource utilization. It takes much less resources to run this slimmed down version, right? These containers, these isolated processes, than it does to run an entire computer inside of a computer, right? One thing we get, and same with the virtual machines, but again, much smaller way, we get multiple versions of libraries, right, running on a single operating system. So now I could have version, what do we have, like Flask version 1.0 running over here, Flask 2.0 running over here, and that's fine, and they're both running on the same host OS. That's great, right? And lower resource utilization, which we talked about, portability and scalability. So this is another thing. And with VMs, you get a similar thing, right? You can create images, and those images can then be used, across other computers, and that's cool. But again, because of they still suck up a lot of resources. So with containers, we get the portability and scalability. And what's even better is they spin up much faster, usually. There can be some big ones, but on average, they're much, much faster than spinning up a virtual machine. And which means you can scale them out to, hundreds, thousands, utilizing less resources and faster. And because they are smaller, we get faster boot times, which I think I just said. Maybe I'm repeating myself. But anyway, hammering the point home. So talking about cons. So cons are possible increased complexity. So containers, right? Just because they're smaller and slimmer and more scalable and all these things, we also get a potential for increased complexity, and which we'll get into more and more, right? In this session, we'll just spin up one Docker container, but once we start talking about how do we network these containers together, how do we scale these containers, that's where Kubernetes comes in, and then you get that complexity. And with that complexity, you get an increased cost, right? And that cost tends to come from the knowledge that it takes to orchestrate containers versus orchestrating virtual machines. Is it more? I don't know, maybe not necessarily, but it is niche, right? Someone who knows, these DevOps engineers who are orchestrating thousands of containers using Kubernetes clusters that are replicated across regions of the world, right? It can get very, very intense in terms of complexity. And then monitoring, right? Monitoring becomes really, really difficult because of how many instances you're running of these containers, because of the nature of containers. Monitoring these containers, these isolated processes, can be quite intense as well. And there are plenty of libraries to handle that, but nevertheless, that can definitely be quite intense. Okay, so I want to just stop. Are there any questions before we move on? I threw a lot out there. Cool. Okay. So moving on, why use containers? So we've all heard this buzzword microservices, and I'll use that here. And we'll talk more about that probably in the next session where we talk about Docker Compose, and definitely when we talk about Kubernetes. But just know that smaller services, right? What microservices are these smaller services. It makes it easy to scale and allows for isolated features. So if I want to scale my application or a single part of my application, like I can do that, which is much easier if my application is broken down into multiple smaller services. So what I mean by that is that if my application is all packaged together and there's an API, a single API within my application that's being hammered, but the rest of that, like there's other parts that aren't being utilized as much, right? It is easier to scale out that particular piece of the application rather than scale the whole thing, because you start to get more resources being used by your application when you do that. And that's not a great way to allocate your resources, right? Like, especially if these other parts aren't being used that much, like it's much better to scale the parts that are getting hammered and scale back or keep them the same, the parts that are not. And the other thing that this allows for is really efficient feature, allows your developers to easily be able to work on isolated features, right? So they can be on different release schedules when they're developing. So if one, if one's working on the front end and another's working on the, the API portion, the back end, and I'm kind of spitballing here, but it's very general. But anyway, it allows them to work on different release schedules, right, for features, which is really nice. Whereas before, I don't know if anybody's ever been involved in 16 to 20 hour releases of applications, but it's not like the most enjoyable thing, right? And so containers kind of make it easier to deploy applications, right? And everybody's probably heard of like CI/CD, right? These CI/CD processes. So it makes releases more frequent. It makes it easier to release isolated features and kind of test these features and roll back and so on and so forth. So those are kind of two of the benefits stemming from these microservice or smaller service architectures. Portability, right? So I love containers for sharing code or sharing things that I've done with others, right? Which I'm going to do with you tonight. So I don't care if you're on a Windows machine or a Mac. Now, I will say Docker has some nuances when it comes to the M1, which I've run into multiple times. So I apologize for those that are on an M1 for your potential problems that you may have. And I can't help you because I don't have an M1. But there's a support group online that I'm sure is on Reddit that you can go to for all of your woes. It allows for better collaboration, right? So if they're on a Windows machine and I'm on a Mac or even a Linux machine, that's cool. I share the container image with them and they're able to run that application on their system. And more consistent QA and production environments. Do a time check here. Cool. Okay. More consistent QA and production environments, right? So because of this consistency of, you develop once and run everywhere, it's kind of the container motto or whatever, you're going to get consistent results from your machine to the staging environment and then out to production environment. So it's more predictable how they will react. And I'm not saying it's 100%, but more predictable, right? Rather than having to create these environments where everything's exactly the same. Containers allow you to do that in an easy, low cost, low resource intensive way. And then team agility, right? So now, like I said, because we can focus on these individual features rather than the application as a whole, you can split your team up and they don't need to necessarily be, communicating all the time. I mean, they should be communicating all the time, but you know what I mean? Like if they're working over here, they don't need to be like, I'm going to release this feature. It might break everything. And then it breaks everything and everybody's sad, right? There's less of that in my experience. I don't know others, if other people have war stories. I'm sure you do. But overall, I've found that to be a really positive thing for development. It makes it more enjoyable. Faster development and deployment, kind of redundant, but quicker ROI than with monolithic applications. So we can react faster to users' requests, right? So if a user comes to us and says, I need, it would be great if I had X, right, feature, then instead of being like, well, you got to wait till the next release cycle, whoever's working on that individual feature can actually be like, well, we're going to go try to implement that now, and they can get it out faster to users. And when you're reacting faster to user requests or user wants and needs, that will make your application more successful, and you'll see a faster return on investment in terms of development and all the things that go into creating and developing applications. Okay, so what is Docker? Docker is a container runtime. Okay, what is a container runtime? Well, it's a tool used to automate the building and running of applications in containers, right? So back in the day, I forget what it was called. I'm trying to think off the top of my head. Someone drop it if you know it, but there's a way to create containers just straight on a Linux OS, which is cool. But again, containers can get quite complex. Yeah, there we go. Thank you. Okay. Thank you. So Alex, everybody dropped it in the chat. Thank you, everybody who responded. So Docker is more featureful, right? And allows you to do many more things, and I'll show that in a second. Uses the client server architecture. So you communicate using a client library to the Docker server, and it just does stuff for you, right? So we're using REST architecture, right? It's done, so communication is done through the REST API. You make a request to the Docker server and it does stuff for you, right? Rather than you having to manually do it. So it's really nice. And so the client sends requests to the API, which are forwarded to the Docker daemon, and the daemon then takes care of those requests. I'll show a diagram here in a minute. Now the Docker daemon is what interacts with the operating system to manage those containers. And this is pulled from the Docker documentation. You'll see it there. But so here's us, right? We're on our computers or a server or wherever we are, and we communicate with the Docker daemon, right? We say Docker build, right? It goes and it grabs a container image, and we'll dig deeper into this in a second. But just know that it grabs a container image and it builds it, and then we can run a container off of that image. So we build images. And when we're actually running an instance of that image, that is what the container is. At least this is the terminology that I try to use. So images versus containers, right? A container is an instance of an image. You can do a Docker pull where you're pulling from a remote registry, which also, right, you communicate to Docker daemon. Docker daemon takes care of that for you, reaches out to the registry. The most popular one is a public registry. It's Docker Hub, where all the publicly available images are. And then you can tell it to Docker run that image or an instance of that image, and we get a container, right? And here's the registry here, and you see we've got CentOS. I don't think so. Maybe it's still there, but Redis, Ubuntu, and Nginx, so forth. Okay, so pretty simple in its architecture, but really, really powerful. And we'll get into demo land right now. Before I go there, are there any last minute questions before we do a demonstration? And I'll share the template for this as well as the GitHub repo. Or comment, doesn't have to be a question. Oh, dang it. Give me 1 second here. Okay, so I'm going to share the. All right, so in chat right now, I'm sharing. There's the repo. Now, I will say I have these on different branches. So we're going to be on the section 1 branch. The other 2 branches are still sort of a work in progress. They might work, but I haven't fully vetted them. So user be warned if you try to skip ahead that there might be some typos in the README or like blah, blah, blah. So it's a, but the section 1 branch should be solid. Question?
Yes. You mentioned containers and Dockers, but where does Kubernetes come into the context?
That's a good question. I'm glad you asked that. So once we have containers, right? We can run a single container, which I'm about to demo. But once you start talking about, coordinating multiple containers, networking those containers together, scaling out those containers based on resource utilization or whatever, that can start to become quite complicated, right? And so that's kind of where Kubernetes comes in. So Kubernetes is a container orchestration engine, is what they call it. And what it allows you to do is declaratively define how you want your application to look, define what containers are running, and it will handle the scaling up, scaling down, rolling back, all of that stuff for you. And so it simplifies the process of scaling out your containerized applications and managing those. And there's other plugins for monitoring and all of that kind of stuff. But if you were to try to do that manually, it's just, maybe for a single application, that's fine, right? But as you try to scale out your application, that could become very intense. And that's what Kubernetes is trying to solve. So container orchestration is the key.
Thank you.
Idea there. Yeah.
It's what the term means or implications are. It makes sense though.
Yes. Oh, there it is. I was looking for my Visual Studio Code. This is when you have multiple monitors, things get lost, especially when you use multiple data supports. All right. Great. Okay. So demo time. Can everybody see my screen okay? Do I need to blow anything up?
Looks good.
Cool. And let me go to section 1. All right. So when you clone this repo, and my intention is for people to kind of watch and then go off, and you can do this on your own. But I forgot the Notion template as well, so you can follow along. Give me a second here. Should have had all this up, and I think I did, but I was like deleting tabs so I could clear my workspace. Shot myself in the foot. So what we're going to be doing is containerizing a fast API application. It's a machine learning application. It's not that great, but it'll do. So what we did was we used Profit, which is a library from Facebook, to do a temperature forecasting model. So time series forecasting. I just dropped the Notion template in the chat. That'll take you to the Notion template that I'm currently looking at and following along with. Okay, so yeah, our fast API application provides a weather temperature forecast based on a time window. So we send it the JSON object, we define the time window, and by time window, I just mean like you want to go 6 days into the future or 30 days into the future. It's by days, and I probably should edit this to reflect that, but nevertheless, we give it a window, and it gives us it returns a what amounts to a data frame. And so we can run this application, which we will do first. And let me say deactivate. Okay. So we're going to run this application locally first. We'll show that, and then we will run it in a container and show that the process of both writing a Docker file, which are instructions on how to build a container image, and then also the commands to run a container. So clone the repo. So the first thing we need to do is, and if people want to see this application, by the way, I can show just the main part really fast. And if you want to dig farther into it, you can. If you're familiar with web frameworks or even fast APIs, it's a fairly simple application, even though for some that are not familiar with looking at this, it can seem quite complex. But we just define some endpoints. We have an endpoint called hostname. We have an endpoint called predict. The predict is a post, right? We send a post request to this endpoint to get our prediction. The hostname one is just simply so we can make sure that it's working, and we use the socket library to return the host name where this application is running. And we want to do that because I want to show you running on bare metal, or in this case on my laptop, versus running inside of a container. So here we go. So we'll create our requirements file, which is a file where our Python dependencies are. So we go txt. So we can define our Python dependencies here, and we pin the versions as is good practice, right? Okay, so we're going to create a virtual environment inside of this base folder. So we say Python -m venv and .venv. I do dot when I create virtual environments so that they're hidden. You don't have to do that. I just do it out of habit. I like it. It's not a requirement though. It won't change anything. It's just we need a virtual environment. But if you do change this name, be aware that the command will be slightly different for activating your virtual environment. So that takes a minute. It's actually been taking longer than I remember virtual environments. And by the way, virtual environments are isolated areas for, and it's usually best practice to do for when you are writing code. So we can do these installs here without polluting our general namespace, right? Or our dependencies on our base Python version. So this isolates it off so that we can work with Python in an isolated way, and we can bring them up and we can do whatever we want. We can destroy it, and it doesn't change our base installation. Usually a good practice too. Another question?
Yeah, you mentioned you were talking about something, and you said if we change the name, what name were you referring to?
Oh, right. So here, if I changed it from, so notice that it wrote a directory called .venv. So this contains all of the packages needed to run our virtual environment. But I could also name it like blah, and then it would create a directory called blah. So and so when we want to activate our virtual environment, we do source .venv, right? And in the case of blah, it would be blah. Oh, here we've named it .venv. So it says source venv. Bin activate, right? And notice here that we've now activated our virtual environment, which is an isolated space away from our base installation. So now we can install these packages without, bloating our base installation.
Yeah, I guess maybe because I'm not familiar with the VEN, the -MVEN. Is that that means create a virtual environment, and you just happen to use the same name? So this is that a keyword or to the -M argument?
Okay, good question. So the -M argument allows us to run commands, right? And venv comes prepackaged with Python. So I'm just saying run a command venv, which is virtual, short for virtual environment. There's tons of other ways to create virtual environments. I'm just using the base here because it's simple. And then the name of the directory, right?
Same name as the command, and that's where I was getting confused. Okay.
Yeah, sorry. Yeah, it's kind of just what I use. I maybe could have named it something else, right? But like Docker env or something like that.
My Ven.
Yeah. Whatever's descriptive and makes sense to you, feel free to change that. That's arbitrary. Cool. Good question. And okay, we'll go right. Okay, so we've got our requirements file. I've created my virtual environment and I activated my virtual environment. This source then been activate. So now I will install, right, my requirements. And to do that, we can do a pip, which is our package manager, install, and we actually do a -R, and we can specify this file. So it recursively goes through this file and reads line by line and installs all of these for us. So we're not having to type them out manually. Okay, and then we just, we can keep track of our requirements much better here. Now there are other things like poetry and so forth that are more complex, but this is not about package management, it's about Docker. So we're just keeping it super simple here. So we go recursively go through our requirements txt, install those requirements. And that'll take just a second, it's not that long. Okay. And we also need to create, oh, Scott has a question. Yes, Scott?
Yeah, so how, with your requirements.txt, how do you know what packages to put in there before you run your application?
That's a good question. Yeah, so in this case, I'm utilizing some dependencies and I knew what those dependencies were. So you know, fast API, it's anything that's not included in the base library is usually what you're putting in that requirements.txt. These are your third-party libraries, right? External to the base Python. So Python comes prepackaged with tons and tons of stuff, but there's also stuff you want to use outside of that. So these are third-party packages. To find those, there's a couple ways you can do that. You can Google it, but all of them are kept at PyPy. Forget what it's package index, right? Python package index. So if you go to pypy.org, you can search projects, right? And you notice there's 400,000 projects here. Now, do be careful. Make sure that you're looking when you go to some of these projects, right? So we'll go Fast API. Take a look at that. So here's Fast API. Here, this is the correct one, by the way. Crazy how far this library has come in such a short period of time. I'm trying to get the guy who wrote Fast API to come speak. Hopefully, he'll agree. But notice, I usually look at stars, right, and see how many people have starred a package on GitHub. If I've seen that there's a lot of interaction with this package, usually means that it's pretty safe, both security-wise, but also that it's not going to be deprecated anytime, or I should say abandoned, not deprecated, but abandoned, which I've experienced. So my famous story is I was working on a project and we used a package and it was really, really cool as an API package and we loved it. And after we built the entire thing, the package was abandoned. And we had to rewrite all of our code into a different package. So that was my lesson, right? Always look to make sure that it is a popular package. Another way you can do that is has it been maintained? So look at the last commits, right? So in this case, the last commit was yesterday, right? And Fast API is very popular, so we know that, but there's other ones that are less popular. Make sure that they're being maintained. This can also be a security vulnerability. If they're not updating the dependencies within this package, those security vulnerabilities can then be leaked into your application. So all of those things can help you evaluate whether a package is good. And to find packages, I recommend just searching in Fast API or just Google.
Okay, so like in this case here, I can go to in the app folder, I can go to the main.py file and see that you're using Fast API and Pydantic and a few other things, and that's where I would maybe grab those from if I didn't know.
Yeah, and usually the requirements, I'm just doing this for demo purposes. Like usually this requirements file already exists, right? And as you find libraries that you want to use in your own code, you would just add them here. So I did this for demo purposes, but usually this file either already exists or you're writing the code, so you know what the dependencies are, and you would create this file here.
All right, cool. Thanks, man.
Yep. And another question?
Can you share that link to that PyPy index thing that you had? I can't seem to find it.
Sure. I think that's right. Yeah.
Oh, it shows up differently than. Oh, I'm spelling it PY instead of PYPI.
Yeah. Python package index. So that last one is an I. I used to have a friend who thought that was an L. So he kept, like, in our stand-ups, he'd say Piple And everybody's like, what's Piple? Like, what's that? Yeah. Yeah, no problem. Okay, so we've got our requirements. We've installed our dependencies from our requirements file. Now what we want to do is I happen to need a, that's API link, yes. I happen to need the way I designed the application, I need an environment file. So this is going to contain environment variables that are needed, and here it's only one, but in general, there might be more environment variables that you need. Oh, that's not past API Python. That doesn't happen. Okay. Oh wait. Okay, cool. Someone else got it. Great. Thank you. Environment variable. So we need to create this environment variable, and the environment variable points to the path where our data lives, and our data just lives here in this data file, right? And this will all make sense why I'm going through where everything is in just a moment when we talk about the container. And by the way, I'm thinking we might go over a little bit, so I apologize for that, but this is being recorded, so you can always catch the rest of it if you need to go once we post it to our YouTube. Okay, so what we need to do is follow the directions in the app directory. We need to create a .env file. So a .env file is just a common file where you store environment variables that might be used. In this case, we're using an environment variable called Raleigh temp path, and we're just feeding in the temperature, the path to, or the name of the file, the CSV. And if you want to look where that is, if you look in the, no, not the models, in the core config, you can find that and other environment variables. And I highly suggest looking, this is Pydantic, so I don't want to get into Pydantic, but you can see here that some of the variables that I've defined to make the application work. I've defined some paths and things in here. So definitely look more into that if you're interested. So, okay, with that, we have our environment variable that we needed, our environment file, we have our requirements, so we can run it locally by just running this. Uvicorn is our server, our web server, and we define where the application is. It's in app.main, and we're running the app. And reload just means that it will read any changes that we make. We don't have to have reload on because we're not making changes to the application. But if you want to not have to stop and start your application as you're developing and making changes, you can add that reload flag, and it will automatically restart itself as it sees that changes are made to any of the files in the application. So we'll wait for that to fire up for a second. It's starting our reloader process right now. And another question?
Yeah, what was the Uvicorn?
Yeah, so Uvicorn, so, okay, so there's a little history there. So there's something called WSGI servers, and there's actually, they're ASCII servers now, which are asynchronous, but nevertheless, so Uvicorn is a web server, and we need these WSGI servers because Python isn't natively able to speak the language of the web. And so these servers allow Python to actually, for us to develop Python web applications. So we use WSGI servers. There's plenty of other ones. Of course, now that you're asking the question, I can't think of all of them right now. Gunicorn is another very popular one. And most web frameworks within Python come with a development server as well. But we need these servers to be able to talk back and forth, between, say, like browser and other APIs and that kind of thing, because Python isn't natively able to communicate using web protocols.
Okay.
Good question.
Yep.
Okay. Yeah, it's more complex, and if you want to read up on that, Real Python has some good stuff on that, or you can dig deeper. Yeah.
Is that a separate install?
And so when we click on, we now have. Oh, sorry.
So
it's one of our. It actually is it part.
Is it built in?
So it's a third party.
Uvicorn.
Yeah, third party install, and there's. Yeah, and there's tons to choose from. Like I said, this is just one of many. It's a popular one though. It's a good one. Production ready. Yeah, so it's an ASCII server. Asynchronous. or the A stands for asynchronous. Okay, so what I want to show you now is not Fast API, but this. So one cool part about Fast API is you actually get API documentation built in. So you get Swagger documentation that comes along with it. You can see there's several things we defined, right? I kind of defined all of this stuff, but you get this nice automatic documentation. And at the docs, and I actually have the base path redirecting to docs. So you will go to docs, whether you type docs or whether you omit docs, it'll still take you to the same place. And we can actually test our application from here as well, right? So our API is well documented, and we can send requests to it. So we can try it out. We execute. So this is just that get, right? That host name extension. So it just gets the host name that we're currently running on. And here you see our host name is given. We get the response headers, so on and so forth. And it actually also produces the curl request. So if you wanted to do it from the command line, right? We could also do that. So we could open up a side terminal, and I copied that command line or the curl request. Hopefully this fires up in a second. Go ahead. There we go. And we'll hit that, and notice that it gives us the same response there. So this is great, right? We've got this API documentation up and running. But what we're more interested in is this predict. Right, so what we can do is also try that out. So we have this prediction window set to 0, I'll set it to 30, which is days, and we will execute that. It'll think for a minute about it. And go ahead, little guy. I should have spent less time on the Fast API and more on the containers. So I'll get into the containers right now, but I'm just showing this to you. So here you see what our output is. We get a data frame. Well, what was a data frame is now a JSON object that produces, here's the dates. And if you scroll down, you eventually get the temperature predictions, right? Now, if you loaded this up, you could load this back into a data frame. And when I say data frame, I mean, I'm talking pandas or, potentially anything else, Spark or whatever, but and you'll get a nice, representation of this data, not JSON, but an actual table. We're not going to do that right now. This is not for data frames. This is for Docker, which I still haven't talked about Docker, and we will get into that right now. So cool. We know our application is working. So this is my workflow. The reason I kind of wanted to show you this is because this is the workflow when I'm building something like an API. I will usually develop locally first, test it, it runs, cool. Then I containerize it. You don't want to get into the cycle of building, then running your Docker container, then failing, then redoing something, then having to build, and then run, and then find out it fails again. That is really time consuming. So when you're developing, I recommend developing locally first. Once you know it's working or you have a working representation, then going to the Docker container, because it's much more difficult to debug a container than it is to debug locally. Okay, so we're going to create our Docker file, and I'll explain what that is. So a Docker file is the instructions, and it is called a Docker file, and contains the instructions for how to build a container. So we name it Docker file, and notice it gives me a nice little Docker representation there, and then I will paste what's in this Docker file. So we're going to go through this Docker file kind of line by line real quick. Okay, so we start with a base Python image. Now this is another container image that I'm able to build on top of. So you don't always have to build from scratch. So this Python container is a Debian container. I think it's Debian 11 or 12 container that is already built and lives in Docker Hub and is publicly available. In order to pull that, right, all I have to do is say from blah. Now, if this container exists in Docker Hub, the daemon will reach out to Docker Hub. It will say, hey, do you have this container? Docker Hub will say, yeah, we got that. It'll send it down from Docker Hub, right? And then we now have that container image living locally, and then we can build on top of it. So we just say from. So think about inheritance, right? It's kind of like classes in programming, right? I say I'm inheriting from a base class to create a new instance of the class and adding things to it. So I'm building on top of that class, adding more functionality. Let me open this up real quick. Another question?
This Python container, it's
Yeah.
better to specify a version number, or is it like latest, like to avoid, to get an update always?
It's a good question. Yeah. So they keep it very up to date. So the Python, the good folks at Python, I don't know, whatever it is, the Python Foundation or whatever, they maintain these containers, keep them current. So there is a Python latest. The latest is what, 3.12 or whatever we're at now. I pinned this version because this is the version that I use to develop my application. So if you're using Python 3, in this case 3.8, you also want the container to be a Python 3.8, right? Because you don't want to have some weird change that happened between 3.8 and 3.9 or 3.11 or whatever, right? You don't want that to affect your application, which is part of what's so great about containers. I can specify a version inside of the container, and it doesn't matter what's happening outside the container. It's not installing on my system. It's just a container, an isolated process that's running a specific version of something, in this case, Python 3.8. Does that answer your question?
Cool. Yep.
Great. Okay, awesome. So what we're going to do is we're going to set a current working directory. Now, inside of our container, during build time, or the container, we have a file system, right? And it's not, okay, we won't get into the file system, but nevertheless, we have this as something you'd see in a Linux kernel, right? And so we're able to specify a working directory, and we say our working directory is /opt in this case. Now you can choose pretty much anything inside the container. I go with /opt as a general rule of thumb for applications, and hopefully makes sense to you. Fight me if it doesn't. But so we'll call it our current working directory, right? So every command that we run is relative to this working directory now, right? And this is during build time. So I want you to separate build time versus runtime. Right now we're talking about build time. So during build time, opt, okay? Now we set some environment variables. One is this Python don't write bytecode. So when you're running Python applications, oftentimes it'll write bytecode for like caching purposes and so on and so forth. We put it to 1, so it does not write those files out. You can read more about that. That's just convention. Feel free to Google that. Environment variable data dir. So this is just an environment variable that we use actually inside our application. So I set that to /data. And then we define a port, right, which we also use inside our application. This isn't actually like setting anything on the container itself. Now this is going to get very meta, and I understand this is very complicated. It's going to take repetition to understand like all of the nuances of what I'm talking about now, but just bear with me. Okay, we'll see some stuff in a minute. So we need a port number. Now all of these environment variables I'm specifying here will be available at runtime to my application and inside the container in general. Okay, so I set these environment variables here. I like to do that as best practice. And then when we build the container, I like to keep everything up to date. So I run an update and upgrade and then clean to make sure that my system dependencies are fully up to date based on, in this case, it's going to be the apt package manager that comes shipped with Debian or Ubuntu or anything like that. We install our Python packages. So just as we did before, what we're gonna do is all of the statements like copying from outside in are relative to where the Docker file lives. So in this case, our Docker file is in our base directory. We're gonna copy in our requirements file, which is relative to here. So we just do we can just say requirements.txt, copy that into our container image. And then we can install requirements into our container image. And then I remove that requirements file because it's not necessary. And then we can also copy our app directory into our relative directory, which is the working directory, opt. And we put it in a directory called apt. Forward slashes, very important when you're talking directories. If you don't do that, you're going to run into a weird error. And I'm just saying this from experience. You can run into this weird error where it creates a file called app, right? Slashes matter. Make sure they're there. One thing to note too, you do not need to make dir inside of an image. If you say copy this to here, it automatically does that. So it will create the directory if it doesn't exist. It won't error out with a directory or file does not exist. It'll automatically create it for you, which is part of why that file that when you have it like say like no slash, it fails silently because it creates the file for you. It doesn't say it doesn't exist. So make sure if you're copying a directory and you want it to be a directory inside, add that slash. This expose command doesn't actually expose, which is not intuitive, but it does not actually expose the port. It's just purely for documentation for anybody who's reading this file. They know that this should be run on port 8000. And I have another question. Go ahead, Wes.
Yeah, I was just wondering if so you copy the requirements over and then you copy the app over. Does that order matter, or could you do it vice versa? Yeah.
So you mean copying the application in after copying the requirements and installing them?
Yeah.
Like that order? Yeah, okay. So order does matter. But in this case, like the application, until we actually run it, it's not going to fail. It's just copying files from one place to another, right? But one thing about Docker files, and I'll say this, when you are building a Docker file, the Docker is smart enough, and this is one of the features, to cache. So each of these creates what's called a layer. Okay, so Docker files just know Docker images are made up of layers. So a lot of these, the run command, the from command, those types of things, they create layers. And so what can end up happening is if what you want to do is go from things that change least often to things that change most often, because this is executed in order, it's caching these steps. So if you had your dependencies listed after your application code, if your dependencies change for any reason, or sorry, if your application, sorry, I'm backwards on that. Your application code will change frequently. So if your installations are after your copying in, constantly be copying in the application code and then reinstalling the requirements every single time you build the Docker container. Because we have them set before our installations, these will change less frequently than our application code, and therefore this layer will be cached, and it'll make our, basically it's everything from here beyond will be executed. Does that make sense in terms of caching?
Yeah, that makes a lot of sense. Thank you.
Okay, cool. Yeah, you're welcome. I usually think about it, as weird as it is, use SHA-256, right, to hash the layers each time something executes. And so when that hash changes, it basically executes it from that point on. Wherever the hash changed, it executes the layer or the build from that point on. So blockchain is kind of similar in that regard, right? We know that everything should be the same from one point down, right? And if anything changes, we know that that's not correct. So it uses a similar idea here in building Docker containers, where it hashes out the layers so that it knows, hey, oh, if something changed, I know I need to start from that hash and build down from there, because nothing else changed above it because the hash is the same. Kind of more technical maybe than we needed to get, but hopefully that was helpful for somebody. All right. Cool. So this is our Docker file, our instructions for building. Oh, we have another one. And go ahead. Question. Another question? Someone have a question?
I have one.
So how we say?
Sorry.
Yeah, go ahead.
So the UVCon, the package is part of requirement.txt, right? That will be installed while in the line number 12, right? Line number 18.
Line number 18 here. So yeah, this is where all of our requirements from our TXT are installed.
Yeah, UVCon is there. Okay, I'm good.
Yeah, UVCon is that. Yeah, it's correct. It's a third-party package, so that's where it will be installed. Yeah. Any other questions? I know there was 2 hands that got raised. Okay, cool. Okay, So we're going to go ahead and build this Docker image. And to build our Docker image, we can do Docker build. Okay, we use Docker build. This is the command. So Docker the Docker CLI will be installed when you install the Docker engine on your system. And we actually get Kubernetes for free with Docker engine, which is super sweet. So that you'll also get that kubectl, kubectl. But so that's later. Let's not. But so we say Docker build. This -t is a tag, so we can tag our images with names. Okay, and the naming convention depends on what you're doing. We're going to keep it very simple. We're storing our image locally. So I just call it docker-demo. I put a colon and I put a version number. This is very, very common. You'll see it a lot in a lot of Docker images that you're pulling and building and so forth. So Docker build, tag it as Docker demo. Then you see this little dot afterwards. We say, because we're in the directory where, and because we're in the directory where our Docker file exists, we don't actually have to specify a path, but that is the path to our Docker file, where our instructions live. So if that was somewhere else in like app / Docker, like we can build it from a different directory. We do not need to be in it, but for simplicity's sake, I'm saying it's just relative to where we're at. Also note that if it's called Docker file, you don't need to specify the file name, but there is a -f command. So if you needed to say like dockerfile -.dev, and then specify a different one called dockerfile.prod, right? We can use this -f command and put that here, dockerfile.prod, and then the dot, right? But anyway, keeping it very simple, we put dot, we're building it from our Docker file, and we let it run. Okay, so it's gonna spit out a whole bunch of stuff. Here it's pulling, and I actually pulled the image before, but it would pull that Python, right? Notice we're installing requirements, right? So here we're doing it's on step 3, right? Notice that it's cached. So this is because I did this before just to speed things up a little bit. But a copy in the requirements.txt, and then we install our requirements. And let me see here. So while that's building, so again, it's spitting out things that we've seen before. But what I wanted to show you, you can actually come into, this is the Docker desktop GUI. And what we can do is come in here, and I specifically looked for our Python, right? So here you see, this is Python 3.7. Where's that 3.8? I'm not using Bullseye. Where are you, image? Let's see if we can find it. SQL Server, ML and Lens. So all your images will be here. I have 1 million because I was doing stuff with Kubeflow, and I have 1,000 images, so it's gonna be really hard to find stuff. Here's our Docker demo, right, being built now. I actually built it earlier, so that's why I have something sitting there, but it's being built right now. And we can come in here, and you can do this with any image. So even if, let's do it with a random image. So if I go to Python, and I look for, let's go to this 3.8 Bullseye container image. If I come here, this is a cool new feature where it analyzes the image for vulnerabilities. Good Lord, there's 206 packages. You can see images that are used to build it, right? And then you can also see the image hierarchy, right? So these are all the images that it inherits from. And so if we do that with ours, if we go back to our Docker demo container, I'm sorry we're over, by the way. Hopefully this is interesting to you. We're almost done here. Containers, no, not containers, images, and that demo. It's lagging a little bit on me. There we go. So we look at our Docker demo, right? We can see all of the things that are executed, right? And you notice here that from Debian, oops, what the heck? we can see that it inherits from Debian. Yep. Okay, it's done, and we're going to run that, and then we'll be all set. But hopefully it comes back up. But you can see that it inherits from a Debian package or a base container, which in turn the Python container inherits from that Debian container, right? And then we inherit from that Python container. So it'll list all of that stuff. This is kind of a new feature. I think it's in beta, so this isn't totally weird that it's kind of bugging out a little bit. But I think you get the idea. There's a lot of cool stuff in Docker Desktop, and I'm going to do a short session, a separate session on Docker Desktop. But there's tons of stuff to be shown there as well. Okay. Now that our container image has been built, we're going to do a Docker run command. So remember, we have a container image that we saw that I just showed you in Docker Desktop. You could also get it by doing Docker. You can say like Docker images ls, and then you can grep Docker demo. There it is. And we see Docker demo here. It rendered kind of weird, but I think you get the idea. Our Docker demo container is right here. It's 485 megs. It was built about a minute ago, yada, yada, yada. And notice the version number that we put after that colon is represented here as well. Now we're going to use our Docker run command to run an instance of our image. So we say Docker run. We put a --rm because once we stop the container, it'll automatically remove it. That is not the case if you don't have this flag. I put this for convenience so we don't have to go back and delete it out after we stop it. The port. So here is where we actually specify the port. So the host and container port, right? So we're binding port 8000 to port 8000 inside of our container. So we have our application running on port 8000, which I actually specify inside the application. It's not specified here, but inside the application. And then we have an env file. So we grab that .env file that we created earlier, which is here. Okay, so this is the .env file. So we're able to feed in external environment variables into our application. So if you want to change those for any reason, like if you're changing between prod and dev and whatever, you can have different settings inside of this env file that you can feed into your application externally through this flag here. We mount. So a mount is very important. We're mounting our data. So we didn't notice in our Docker file, we don't actually copy the data in anywhere. Data does not live in our app, in our Docker file, and that is best practice. Docker files by nature, or Docker, I should say, containers by nature should be ephemeral, meaning I should be able to shut down a container and I don't lose any state, right? So they should be stateless. And because they should be stateless, that is why I'm using this -v, which stands for volume. I'm mounting my current working directory /data. So I'm mounting this here internally within the container when I run it, and it will automatically create the directory just as it did when we put it in the Docker file. It'll create that directory automatically for us. It does not need to exist already. I give it a nice name, otherwise it'll name it something like, you know, veritable quandary or whatever. Right? It gives it random names if you've ever experienced that with other things. So we give it a nice human readable name called Docker demo, also predictable, so that we can do things with it. And then we have Docker demo colon 0.1.0, which is the name of the image. So this is the name of our container instance. This is the name of the image that we are creating a container instance from. Hit run. I know that's a lot of stuff. I highly suggest you read and look back on this. There's also a couple things I've noticed that I didn't go over in the Notion template, so I will go back and give better explanations on that stuff. Now, notice that we're running. It looks sort of the same, except notice that we're not on localhost. We're broadcasting right across all ports, which we all addresses, which we've specified here, right? You can specify to do that in the Uvicorn WSGI server, or I guess ASCII server. So it's broadcasting there on 8,000. That is internal to the container. This is not on the host. The only reason we're going to be able to access this on the host is because we bound the internal port 8,000 to 8,000 on our host, on my laptop. I can bind it to whatever, right? Of course, assuming it's above whatever that threshold is, right? But as long as it's not a reserved port, I can bind it to any port I want, right? On my system. Internally, I have specified 8,000, right? But externally, I could bind it to anything. So, so what we can do, because we bound it to our local host on port 8,000, we now have access to the internal application running in the host, and we go to localhost 8,000, and once again, we're able to access our application. And notice we got some log output here with a 200 OK on a GET request, which is what we just did. And we can try out our application by specifying our time window once again. I'll maybe do 15 days this time. We'll execute that. And we should see a post. Here's our post request that we just made. And that should come across here pretty quick. Takes a minute because this is not a performant application. It is a dummy application. But nevertheless, we get the same output that we would expect, which is the same output we got when we were running on our just running on our laptop. So this is running inside of a container. And we can see that if we go to containers that are running, oh, I have a hash here. I have a filter on. I'll take off that filter. Holy crap, I have a lot of stuff running, but nevertheless, you see our Docker demo here at the top running for the last 3 minutes and running on port 8,000. Which we could click on and will also take us to our application. Okay, so it's a lot. I know it is a lot, but that's why I kind of staggered these meetups. And I'm sorry we're 20 minutes over, but this is kind of why I've staggered these meetups, is because there's a lot of information to be said, and you know, it's going to be. I want you to absorb it. So I want you to go back and do this. I want you to go to the Docker documentation and look at that. I want you to go to the resources I gave you, look at that over the next few weeks so that you can get accustomed to this, because we're going to take it a step further next time. And I see questions. I know I'll get to them in 2 seconds. Next time, we're going to talk about Docker Compose. Okay, and in Docker Compose, we start thinking about how do we break this application out into multiple containers like we were talking about in terms of smaller services, microservices, and network those together so they can talk to each other. Okay, so we start talking about container networking next time, and we talk about how do we break those down and create an application that is a little more compartmentalized. Whew. Okay, Shuhong, hi. Okay, let me get to the questions. I know there's hands raised. Let me look at the hands that are raised. I think they went away. Did you put your hands down? I don't know. If anybody has any questions, feel free.
I just have, so you have planned to show sometime how the cube, how we can deploy this into Minikube or Kubernetes environment?
Yes, correct. So this one was just a single Docker container. Next time we'll talk about Docker Compose, break it out into smaller services, and then the third session, well, there's kind of an in-between, a 2.b or whatever, where I'll show you something called dev containers. So how can we utilize containers in our everyday for development purposes? But then the official third session will be Kubernetes. Yeah, we'll take this exact same application, we'll deploy it on Kubernetes and scale it up and down. It's pretty cool.
Okay, thank you. Yeah.
Yes. Another question in the chat. Talk about the general logic, how you choose different versions of the libraries. There are so many different versions. Yeah. So are you referring to the Python dependencies, or are you referring to the Docker containers or the Docker images that we build on top of? There's two different, both, okay. All right, so when I'm using, so it depends, right? So I'll start with Python. When I'm deciding on Python dependencies, first I just go look for stuff. Like I get lots of newsletters. That's one thing I'd highly suggest, and I can suggest just the Real Python newsletter is amazing. So every week they send out a newsletter with a bunch of blog posts, a bunch of new articles that are, and not necessarily just on Real Python, but all over the web. They just collect them, send them to you. That's a great way to discover new libraries. And then they just put new libraries in there at the bottom. They're just like, here's some cool libraries. And you can just go look at them. And that's a great way to discover new packages you may have never seen before. Because like you saw, there's like 400,000 packages, 400,000+ packages. So getting those types of newsletters and just being curious is how I find new dependencies or things I want to use in my application. In terms of pinning those, that's where that PyPy comes in, right? So if I go to pypy.org and I go back to fast API, well, you'll notice that we're at 0.95.0. So wherever I start using this package, I pin it there. And I usually pin it by the 3rd decimal, which is the bug fixes, right? So the minor version, this can have other changes in terms of features, which can break stuff. But usually the bug fixes do not break stuff. They just address exactly what they're meant to, bugs, which I do want. So when you see how I put the star here, this leaves this as variable. So I pin it to 0.81. Whatever. Notice that we're on 9.5. I haven't updated it, right? Because I know it works on 8.1. And that needs to be explored. If you're going to update your versions, make sure that you're exploring what's new, what the breaking changes are. And how you can do that is you go to Git, the GitHub, or the GitHub, the repository, right? And they'll have what's called a change log there. And you can see what things are new, what things have changed since the last version that you're on. And there should be, I don't know where that is here, but anyway, there's usually a change log that you can see what has changed and changes that are coming. So you can decide for yourself, do I want to go to the new version or am I good staying here for a while, right? So that's Python packages. I just discover them. Whenever I start developing, I just pin them to that version. If I ever decide to upgrade, I evaluate, make sure there's not any breaking changes, right? So I kind of do development work and test and make sure. For Docker files, you try to use Docker files that are from the official Docker files. So if we go into Docker Hub, dockerhub.com. So we go into dockerhub.com and explore. So you can see that there's a Docker official image or verified publisher. If you check those, these are how you know they're from, right, Ubuntu, right? It's the Docker official image. So these are verified, similar to your Twitter blue check mark. Anyway, you know that this is the right image, right? So that's how I validate that I'm building on top of the right thing. And what one am I going to use? Well, whatever one I need to use at that particular moment, right? Whether that's I need a Redis, or we'll be using MySQL in our next talk. So MySQL, you can also use MariaDB, whatever. So I try to look for official images because users can post all kinds of stuff on here, and I'm not necessarily okay with that. I don't want to use something because it could have bugs, could have malicious code. So just be cautious. Now they do security vulnerability scanning on here. So, but nevertheless, just as an extra check, just be aware that there's these tags that'll tell you whether they're safe. Answers the question. Another question? Yeah, go ahead.
Yeah, hey Chris. So in the upcoming Docker sessions, are we going to go over cases where we have our data like outside of our machine? Like at work, I work with a lot larger data set, and I'm assuming I can actually push that to Docker, or would that be the topic of another session?
Yeah, it's a great question. So in this instance, and I'm glad you brought that up. So in this instance, what we did, right, was mount our data, and with very small data, right? Obviously, because it's literally in the repo. this tiny data set, right? It's a tiny CSV. It's only, what, 883 rows. But if you have a large data set, or if you have a database, how do you connect to that? Well, I've actually set up the next demos to simulate what it would be like to have an external database that you're connecting to from a Docker container, like a Docker environment. So yeah, I'm going to go over that, how you might do that and what that might look like. But no, it's a great point, and yes, that will be covered.
Okay, thank you.
Yeah. Awesome. Good questions. Hopefully everybody got something out of this. Are there any other questions before we jump off? Half an hour late. All good if you have more questions. I'm happy to answer. But
well, thanks for doing this, Chris.
yeah, absolutely, absolutely, and I'm excited that everybody's excited. So if you want to continue down the container path, next time, like I said, will be Docker Compose. To be, right, like the kind of in between will be dev containers, which are kind of a newer thing from VS Code. I think they're really cool. I'm advocating for them, so I can show you how those work. And then Kubernetes will be our final presentation, the climax, right, where we show you how to get this application out to a Kubernetes cluster, which comes packaged with Docker Desktop. So once you install Docker Desktop, you get Kubernetes for free. We'll be just working locally. Okay, you'll have everything you need. Oh, one more question?
Yeah, sorry.
Yeah.
So normally, I'm not into much Python. I'm just learning now. So normally in Java, you compile the classes into a jar and you deploy, right? And copy the jar into the container in the Docker file, you copy that. But in what I observed here in Python, you copy the entire file into py file into the OPT folder, right? You're not compiled into any form. So that is the way the Python work?
Yes. So you have stumbled upon the difference between an interpretive language and a compiled language. So
Okay.
yes, yeah, that's part of why, and circling back on debugging, that's part of why I said don't go straight to container, right? Make sure you're debugging locally first, because runtime errors or compilation errors will happen during runtime. And so when your application runs, like, you're not going to run into those errors until the application's actually running, and then it breaks, and then you're inside a container, and then you have to go back through the process of, like, right, rebuilding and redeploying. So make sure your application in Python works locally before you package it into the Docker container. Otherwise, your development cycle will be much, much longer.
Okay, thank you.
Yeah. The recording will be uploaded to our YouTube channel. So Portland Python Pirates, you should be able to find it on YouTube, and I'll have it up there sometime this week. And with that, I will let everybody enjoy their evening. I hope everybody found that useful. Hopefully I'll see you next time for Docker Compose, and then again for our Kubernetes session. Have a great night, and thanks for coming.
Thank you.
Thank you.